what is the average length of paths in a network, suggesting how connected that network is, how easy or difficult it is to reach from one end of the network to the other endpoint, right? And these graphs can be used to model relationships, not just between individuals, but also among individuals and content, among groups. So groups of individuals can also be connected through networks. So as opposed to looking at the social networks at micro level, individual level, you're looking at much more macro level or social society level, right? Two main concepts that emerge from the application of graph theory on social networks is the structure and the behavior. So how social networks, the application of graph theory can help us understand the structure of that social network. And over time, or when we look at the dynamics of the network, behaviors that emerge in that social network, right? So the key difference, the key point there is the temporal dimension, the time. So for a structure, you're looking mainly at the static network or static graph, a graph that is kind of permanent in space and time. But when you relax the temporal constraint, when you are observing that network over time, maybe every day, every week, or every month, then how that network is evolving, changing based on the behavior. So as the network is evolving, you can also understand the behavioral trajectories. For instance, if you're looking at communities over time, then you can see how communities grow or shrink, how certain things within the communities can have an impact on the network. So if there is a healthy narrative, healthy discourse, and the communities are growing, when on the other hand, if there is false narrative or hate speech or toxic discourse, then you can observe that the communities start to shrink or they start to fracture or fragment. So all those types of behaviors can also be studied. Much more complex behaviors such as social movements, collective actions require both studies of the structure of the network as well as the behavior, right? So behavior could be how collective identities form, how collective identities emerge from a group of individuals, along with how individuals mobilize to form groups, um, and then from groups to crowds or crowds to mobs and so on, and then how the network organization leads to strong collective action that results in maybe a protest or in a social movement. So ultimately, all these concepts can help you develop models of social behaviors or social phenomena, um, to the extent that you can even start to predict um, when a group of individuals could be successful in mobilizing into a social movement. Right. And of course, there are many other examples that we will cover from time to time. Right. But that's some very very high level um, view of applications of graph theory. I've given here an example of how blogs or blogosphere can be considered as a social network. Blogosphere is basically, for those who don't know, is a universe of blogs. So if you are familiar with blogs or vlogging, video blogging, then that's kind of similar to that, right? So how individuals create their blog sites or blog posts, and then various blog sites can link to each other. So in that case, you can consider different blog sites or blog posts as vertices, and the links or the relationships between those blog posts, blog sites can be the edges. Right. Hmm. All right. Any questions? Any thoughts so far? Okay. Good to know. Yep. And again, if you have any questions, even thoughts, or you want to mention something um, that you come across, that this is something that I want to share with the class, feel free to do that. All right. This is a visualization of a network on LinkedIn for a particular individual. So it's not important who this person is, but what is more important here is by just looking at this network, LinkedIn network, you can see that clearly there are two communities or two groups of individuals. Each circle is an individual. Connection is basically if you're connected with that person on LinkedIn, right? So when you look at this network, it gives you an idea that there are two communities or two groups. But what really happens here is as the person switched the job, they are connected to both the groups somehow because they still have the previous affiliations or previous connections from their previous job. But the current job also you have connections. So this essentially tells you how a person, when they move between jobs, they can create these different communities, right? So such type of a behavior is observed from this network structure. So again, those two concepts of network structure as well as behavior are very strongly applicable here. And of course, when we visualize this on a screen, yes, we can see that there are two communities. But later on, I will show you some methods where you can feed the network data to computer algorithms and it will automatically identify those communities for you. Because it is easy to do this in this scale where we only see two communities and handful of nodes. But if you imagine there are billions of nodes in the network, for instance, Facebook network or Twitter network, where you may have billions of nodes, it will be very difficult to just manually identify such groupings or such clusters, such communities. So that's why for scalable analysis, for large graphs or big data sets, you would need those strong graph analysis background. Okay. All right. This is a little bit more complicated LinkedIn network. Again, the same thing. The person in the center is connected to all these different groups. And these are basically, as the person is changing jobs, you can see those connections change, right? So you have one set of connections from your previous company or previous organization, and as you change your organization, you acquire newer connections. And often you may not have as strong connections between the two organizations network, but you may have strong connections within each of them, right? So there may be some shared connections or connections across the two organizations or multiple organizations, but not as strong as within the same organization, right? So that is also one of the principles behind communities, that you have stronger connections within the community or in between the community as opposed to across communities. And those across community connections can be considered as bridges who can somehow broker information across these organizations, right? So this person who is in the center can be kind of considered as a bridge across all these four organizations. All right. Okay. This is a network of blogs, again, based on which blog links to which other blog. So edges are essentially links, and the dots are the nodes here, or the blog posts. So clearly, when you look at this network, you can see that it is bipolar in nature. So there is two very striking groups, very visible groups, one on the left and then on the right. And then you don't see a lot of interactions across, but you do see a lot of interactions just within each community, right? So that's a typical representation of how polarized political spaces are, and social media is just a reflection of that behavior that happens or manifests in the real world. And the same thing applies when you look at Twitter space or Facebook. Then you will see all these different types of polarized views of politics. When you move to email networks, that's a very different structure, right? So we have been looking at various structures, right? Different settings, different scenarios. In email network, you will recognize a more hierarchical structure So you may think that the CEO of the company is probably at the center. They're sending emails to probably the VPs. The VPs are further sending to the managers, senior managers, then down to the managers, and then the employees. So very typical hierarchical structure is observed in email communications. This is a network of several employees, more than 400 from HP Research Labs. And when you throw this on a network visualization, these emails, and you observe this type of a network, right? So again, very different structure that shows how organizations behave in different settings. In a more formal organization, you have this. While you looked at LinkedIn, it was a different structure. We didn't see a very hierarchical, but very clustered group here. Yeah, right. But nevertheless, all these structural differences in the networks are meaningful. They tell a lot about the network, about the users, their positions, their roles, and how coordination, collaboration, and organizational activities are conducted. So having a good understanding of network structure is key for understanding any behavior, right? So these structures help us in knowing who the central individuals are, central groups are, network resiliency points, meaning if you want to disrupt certain networks, let's say it is an extremist or a terrorist network, then to disrupt that, you need to identify who the central nodes or central individuals are, and then you can disrupt with maximum efficiency. Right? How to represent a graph. So we have seen some examples of visualization of the graph, which are easy to look at, but very difficult to represent um, in a data environment or on a computer. So our algorithms or computers may not be able to understand the visualized network, but they would need something to work with. So we represent them using various types of data structures, which we'll cover later. But very typical or a mathematical representation of a graph is nothing but a set of vertices and edges. So vertex set is essentially all the nodes, all the vertices, and edge set is essentially the ordered pair of vertices. So here you have V1, V2, V3, V4. Those are your vertices in this graph, and the edges are marked by the ordered pairs. So V1, V2, V2, V3, V3, V4, V4, V1. Now this is a graph that we don't see any directions, so it does not matter if you write V1, V2 or V2, V1 to denote the same edge. However, if it was directed, then the direction would govern how you write that edge. So if it was directed from V1 to V2, then it should be written as V1, V2 and not as V2, V1. Okay. So as I had mentioned, so two types of graphs, directed and undirected, and we know how we depict undirected graphs. For directed graphs, we just want to make sure that the edge direction is captured in your edge set. Okay, and there are multiple examples from social media I'm sure you're familiar with. So if you look at a graph of web pages, of websites, web page A linking to web page B does not mean that web page B is also linking back to web page A. So those are directed relationships. Similarly, on X or Twitter, you can follow someone, but it's not necessary that they will follow you back. If they do, then yes, it is a bidirectional network or a bidirectional edge. But if they don't, then it's a unidirectional, right? Regardless, it is a directed graph. Okay. So other than directed and undirected, we also see sometimes weighted graphs, meaning where the edges may have some weights. And these weights could depict a lot of things, starting from, say, number of interactions or number of emails exchanged, number of messages exchanged. Uh, Even let's say if you go beyond social networks, transportation networks, you look at road network, then you can think of the delays or the length of the path between city A and city B. If you're looking at a network of flights, so planes flying from city A to city B, the edge could depict the time to fly or time to reach, right? So there could be numerous examples of these weights. And the same graph could have multiple weights on the edges depicting various characteristics, right? So within a social network, you can think of one weight as the number of interactions. Another weight could be considered as toxicity or emotions. So let's say if a person A sends a message to person B and that message had certain level of toxicity, then you can put that as the weight on that edge, right? And of course, we will get to that stage where we will know how to compute toxicity on a scale between 0 and 1 and so on. So that will come later. But for the sake of this lecture, imagine that you have some type of a model or some type of a method that will give you these weights or these scores on the edges, right? And again, the idea is these weights could be any number of characteristics. Could be number of messages or interaction frequency or delay or the bandwidth, lag, etc. or toxicity, sentiments based that is assessed using the content exchanged between the two individuals. Okay. All right, so that is weighted graph. Regularly, if we don't have weights, then we call that as unweighted graph. Which is nothing but a special case of weighted graph where you can assume that all the weights on the edges are equal or one, right? So if you look back at this example where we didn't specify any weights, then you can assume that the weights here are one, right? And again, this is undirected graph, all right? Okay, some more types of graph based on the connectivity. We can call a graph as a complete graph or also known as a clique, where all the nodes in the graph are connected to each other. So it is completely connected. So any two individuals in that graph are directly connected, right? But if you think of social networks, you may not find such a complete graph all the times, right? Because if you think of Facebook, you may have billions of individuals on Facebook, but not everyone is connected to everyone else, right? So in that case, such type of graphs, especially social networks, are not completely connected graphs or complete graphs. These are very, very particular scenarios where you may find a community or a set of individuals within the big network that are connected with each other, right? So you may find cliques within a giant network, but the whole network or that giant network may not be a clique. Okay. So you can see that for two nodes or two individuals, just one edge is enough to call it completely connected or clique. If you have three individuals, then three edges are enough. But as you increase the number of nodes or number of individuals, then the number of edges start to increase almost exponentially, right? So that's another reason why large graphs are not completely connected or not cliques, because then you are looking at establishing that many number of relations with everyone, right? So that becomes too much of relationship fatigue for individuals, which is, by the way, a social phenomena because you have limited bandwidth, limited time. You can keep up with your friends, your family. So that's why there is actually a number defined by a sociologist, Dunbar, who said that in a real life setting, any individual cannot have, or they have on average 130 connections, not more than that. Meaningful connections where you're at least interacting with them frequently. So that's called Dunbar's number. All right. So after complete graphs or cliques, we also have something called a bipartite graph, where you're looking at different types of nodes within the same graph. So far, we were talking about individuals or users in a social network. They are connected with each other. But you can also consider networks or graphs within the social network setting where the nodes could be different types, could be of different types. For instance, you may consider a network of users and their blogs, right? Individuals and their blogs, right? Or another network could be a movie actor network, where you are depicting relations such as which actor acted in what movie. So there are two types of nodes here or vertices. One is the actor, the other is the movie. In the case of the blog network, you have one as the user or individual, and the other vertex could be the blog site, right? Now the question is, why is that important? Like, okay, so we have this graph. What is it good for? Often you'll realize when we are modeling different types of relationships or more complicated relationships, then having bipartite graphs or these heterogeneous graphs where all the nodes are not alike, they are different types. So these heterogeneous graphs come handy in terms of modeling those complex relationships. Right. We will see some examples later in the course where such type of bipartite networks are in fact used to do search rankings or in the search ranking algorithms, right? So think about web pages, how some type of web pages could be more authoritative, some pages could be more hubs. So having two different types of roles for web pages can allow you to use these bipartite network concepts to understand their prestige as a hub or as an authority. Right. So, of course, we will cover that example also in more depth when we get to search engines and rankings, Google PageRank, hits, and so on. That's where we will cover these concepts. But again, the fundamental is this one, which is bipartite graph. So you should remember what a bipartite graph is. So when we get to that concept, you will know what we're talking about. Right? So we looked at different types of graphs. Homogeneous graphs and heterogeneous graphs. So we looked at homogeneous graphs where you have just one type of nodes or one type of vertices, let's say all individuals, all users in a social network like Facebook, versus heterogeneous graphs where you have different types of vertices, and those could be considered as two types or three types, and correspondingly you can call them as a two-mode network or a three-mode network, right, depending on the number of types. We looked at some examples of two-mode network, movie actor, blog and bloggers. For three-mode network, you can again stretch that into content. So a user connected to, let's say, a community and what type of content they are interested in, right? So some type of hashtags. So you can think of a network between users, communities, hashtags or users, groups, hashtags, and so on. And again, the more such information you're adding to the network, the richer that representation is, and it will be able to address that much more complex behaviors or research problems. Okay. All right. How is everyone doing so far? Any questions? Okay. Silence is golden. I hope you guys are able to follow. And again, these concepts are going to be very important. There will be an assignment. Your projects will depend on this. So I would again encourage you guys to pay as full attention as you can. Don't get distracted because the rest of the lectures will build upon this. So if your fundamentals are strong, the rest of the course will be smooth sailing. So again, these are very important concepts for this course. Okay. All right. So on the chat, looks good. Everything perfect. Now we move on to much more complex definitions and concepts within the graphs. So far, we were just looking at types of graphs. Our units were individuals or nodes, but not beyond that. But now we will start to look at groups of nodes. So how we can start to visualize the networks beyond individuals, thinking about their relationships, thinking about groups, communities, how we can identify. So what are the basic concepts around those behaviors? And then we will see what computational methods we have at our disposal to extract these communities, right? So as you can imagine that first we define the graph as a set of vertices and edges. So if we are defining communities or groups within the network, within that graph, then we are further clustering that graph or identifying subnetworks or subgroups. So then we define something called a subgraph, which is a component within the graph or a part of that graph, which is a further refined subset. Let's say we call that as G prime, which is a subset of that graph. And parallelly, if it is a subset of the main graph, then the vertices of this subset will also be a subset of the main graph. And the edges of this subgraph will also be a subset of the main graph. So you can imagine the subgraph represented as G prime, which has vertex set as V prime and E prime, and V prime, E prime are also subsets of V and E respectively. Okay. So if you look at this illustration, if you consider the whole box here as one graph, then you can consider these tiny little graphs as subgraphs, right? When you consider the full graph, you have G equals VE, V where is all the vertices and E is the entire set of edges. But if you focus only on this community or this group of users, then the set of vertices is much smaller, but still is a subset of the whole graph. Similarly, the edge set is much smaller with respect to the whole graph, but still a subset, right? So that's how we define subgraph, straightforward. Supergraph is basically a graph in which G prime is a subgraph, right? So you can consider the whole thing as a supergraph of the subgraph, right? So G is a supergraph of G prime. So now it tells you that the two concepts, subgraph and supergraph. So you can also think of this as a subgraph comes out of a supergraph. So supergraph could be considered as the parent and subgraph could be considered as the child of it. Okay. All right. And we'll come back to this concept when we start looking at group extraction or community extraction approaches, which we'll do today towards the later end of the slides, where we will start defining computational methods to accomplish some of these things that we are discovering, we are reading. Okay, so we start looking beyond individuals. Now the next concept, when we look at a collection of individuals, collection of nodes, is how easy or difficult it is to reach from one point to the other in the graph, right? So what is the path? Is there a path first? And what is the length of that path, right? Often when we go to LinkedIn, we see that so-and-so person is 2 hops away or connected to someone who's connected to you, right? So how does LinkedIn know all of this information, right? So they have the network of everyone. So they can calculate when you're visiting a profile, how far away they are from you, right? So the more you're connected with the rest of the network, the shorter your distances will be to the rest of the network, right? So that's quite common sense. So that's why when you go to conferences and all these events, people emphasize that make sure that you network well. So you increase your acquaintances or increase your network, enlarge your network. And that's the main reason. The more you're connected, the larger your network becomes, and that much easier for people to reach you, people to connect you, information to travel to you. So this is all connected, right? But there is a concept which is called path and path length ultimately, which tells us how far or close two individuals are. So if you consider these two red dots as two individuals who we are interested in, whether they're connected or not, then we can look at this toy example of the network, and then we can see how well they're connected, right? So from the node on the extreme left to the node on the extreme right, you can see how we have to traverse, and there are numerous paths, not just the one that is highlighted in green, but there are many other paths too, which will show you that there are not just one but multiple paths between these two individuals. One is highlighted in green. I can point to many others. So if you just keep following the straight line, you will reach the other end. Another path is when you follow the direction towards right, and instead of going straight, continuing straight or down, you take the diagonal down, and then from diagonal down you can go up diagonally. So that path is actually the shortest path, right? So if you look at the green path, you can count how many vertices will fall on your way. So starting from here, you have to encounter one, two, three, four vertices. If you were going straight, then you will encounter one, two, and three. But if you are going this diagonally, then you will encounter only two, right? So clearly there could be, and in this case there are multiple paths between two individuals. Some paths are longer than the others, but we are always interested in the shortest path, right? So what is the shortest path? What is the quickest way we can deliver the information from point A to point B? So knowing these type of paths are very helpful for social networking companies. So Facebook, you may have seen they try and recommend people to you, like you may know this person or you may know that person. How do you think they recommend that, right? So they rely on these concepts, path length. The closer a person is to you, the stronger the chances that you may know that person through some remote acquaintance or through your direct connection, right? So that's the idea. They exploit this concept to recommend individuals to you. Okay. This also gives rise to very interesting concepts like 6 degrees of separation. Not sure how many of you have heard this concept before, or probably even watched some of the movies that were made on this 6 degrees of separation. But this was a very famous experiment that was conducted by sociologist Stanley Milgram in 1960s, 1967 to be precise. Um, and of course, at that time there was no internet. There was no way that you could just look at Facebook and ask them the data, and then they can just do this analysis of knowing how people are connected and what's the average path length and so on. But they had a very interesting setup where postal mail deliveries were used between two random individuals within the US. And at each point, so the starting point was given an envelope that you have to send this envelope to this person, and they would not be shown, or they would not be given the address of that final destination, but only the details of their job or profession or things like that. So they would need to send the envelope to the next person they know, who is probably in the same area, same geographical location, or in the same profession. And they were free to choose whatever characteristic they want to, which they think can lead the envelope to the closest person in the chain. So at each hop, as these envelopes were traveling, at each hop, there would be a postcard that would be mailed back to Stanley Milgram, and that's how he would know for each chain whether they have those envelopes have reached the destination, or the experiment was just abandoned because people gave up. They got frustrated. This is useless. This is, what is this? So they started with such 300 such letters, and ultimately only 64 out of those made it. So imagine the data sample size here. Huh? So out of 300, only 64 made it to the final destination. And from that 64 that completed the chain, they averaged out how many envelopes, how many postcards they received, right? And the average number was 5.5, and they closely, basically rounded up to 6. And that's how the 6 degrees of separation comes about. So this basically tells the conclusion was that randomly or on average, two individuals in the world are connected within 6 hops, right? So that was a very famous experiment that led to this finding. But when you stretch this nowadays to Facebook, right? Because now it's much easier than setting up envelopes and postcards and mailing and all of that. And you can see how little the sample size was. Still, when you look at this chart on Facebook, you can see that when they calculate the average path length, it centered around 5, but not as close to 6 as it was 1967. It was a little bit closer to 5, or maybe even less than 5, so 4.8 or something like that, which tells us that we are that much more connected as opposed to previously. So then the question is social networking or social media helping us to be more connected, or are we less connected? Right? So clearly the numbers show that we are more connected. That's why the average path length is reduced. But are we really more connected, or we are just connected on Facebook, but doesn't really mean we are that well connected, right? So that's kind of a philosophical, debatable question. Um, but that's what the numbers show. And this experiment was done in just one afternoon, while the other experiment that was done in 1967 took almost 6 months to complete. So clearly we have gone, leaps and bounds in terms of conducting such experiments computationally. So that is one key takeaway here, that computers and information science can help conduct these experiments much faster. The outcome that we get may not translate equally in the physical spaces that we see the behaviors manifest in digital spaces. So there could be a disconnect between physical and digital spaces, but as we increasingly spend our lives on digital platforms, digital spaces, does that difference really make an impact? Right. So that's another question that you guys can think about. How we think about digital spaces, physical spaces, differences between them, similarities, and how one influenced the other, and so on. All right. Any questions, thoughts, anything you'd like to share? Okay. Well, we'll continue to move on. Wonderful. Since we talked about path length, the next concept that we would like to cover is connectedness. Intuitively, any part of the graph is reachable from any other part. Um, Formally, graph is connected if there is a path between every pair of vertices. Um, and then, of course, connected graphs are different from complete graphs. So a moment ago, we discussed about cliques, which are complete graphs, where an individual is directly connected to the next individual or all the individuals. In connectedness, we relax that assumption. We are saying that we will still consider two individuals as connected if there is a path between them. We don't care if the path has a length of 1 or 2 or 3, whatever. As long as there is a path, we consider that graph as connected. But every individual must have a path to every other individual, right? May not be direct, but must have a path. So that is called connectedness or a connected graph. Complete graph, on the other hand, is a graph where everyone is connected to everyone with a direct edge. So the path length is 1, right? So that's the key difference between a complete and a connected graph. So if you want to think about this a little bit more, then a complete graph will always be a connected graph, but not the other way around. A connected graph may not be a complete graph. Okay, so that's the difference. Further, if you think about directions, then you can start to define more specific concepts for strongly connected or weakly connected graphs. So if it is undirected, then we only have one definition, which is connected or not, connected or disconnected. But if the graph is directed, then you can have a strongly connected graph where, considering the directions of the edges, you can still reach from point A to any point B in the graph. But if that's not the case and you have to relax the directions or discard the directions, and then that graph becomes connected, then it is considered as weakly connected graph. Okay. These things are important when we start looking at communities, information flow, narrative contagion on directed graphs, right? So how information flows from point A to point B in a network, and how does the network structure would impact the flow of that information. Because if it is a directed graph and if it is not strongly connected, then you will have challenges where you may not see full or complete flow of information from point A to point B, right? So that network will have information black holes, right, where information goes but doesn't come out. Okay. Stretching that definition further, you can then identify subnetworks or subgraphs within a large graph that could be connected, and those subgraphs will be called connected component. Because imagine for a Facebook network or a network like Facebook, it is very difficult to even imagine that a Facebook network will be connected. That every individual is reachable from every other individual. Probably not, right? There may be some individuals who do not even have any net. They just started their Facebook account and they haven't added anyone. So they will be like isolates or islands in the whole Facebook network. So it will be very difficult to reach them, almost impossible to reach them, right? So a network like that will not be connected. So in those cases, then we start to think of subgraphs. Are there subgraphs within that larger graph that could be connected? So again, that's where we start identifying communities and then test those communities for connectivity and so on. Right? These concepts are also important when you're identifying groups, key groups. So given a big network, you want to know which are or who are these individuals who are completely connected or connected with each other. So that way the information flow is transparent, is 100%. And those are the ones who often help in mobilization or core mobilization for social networks, for protests. So identifying such type of individuals or such type of units or subnetworks, subgraphs are the key to understanding large-scale, complex social dynamic processes like collective action, social movements, protests, mob networks, terrorist networks, so on. Okay. This is a very famous concept also in the web crawling. Because when you look at the web of web page, like web pages, right? Network of web pages, you will see that this is a directed network. So again, not every page is going to be linking to every other page, which essentially tells us that it is not going to be a connected graph. But there might be some components within that graph that are connected. So when you are writing your own crawlers, or in this case, when Google or Yahoo or other search engines were writing their early days, in their early days, when they were writing their own crawlers to index the whole web, they were struggling with this concept that where should we start our crawler so that we can guarantee maximum coverage of the web, right? So if you start from a place in the network which is an island and isolate, then you're guaranteed that your crawler will get stuck on that island or on that set of web pages and not going to go any further, right? In order to make sure that your crawlers are getting maximum coverage, you need to understand how the web structure looks like and then start from a point where you have the maximum coverage. So it turns out when the whole web network was mapped after repeated crawls, several hundreds of thousands of crawls. And again, this is very early on. You can see that the publication date of this paper, 2000s, 25 years ago. But again, it is still very relevant because till date, the web structure is still the same. It has grown by leaps and bounds, but it is still the same. But when you look at the web structure, after repeated crawls, it was found that it had bow tie structure. So there were a set of pages or set of websites that were linking to the central core of pages, which were further linking to these other pages, meaning the information or the network direction was from left to right, suggesting if you start your crawler somewhere in the green area, then you're only going to get stuck here. The further you go left, the maximum your coverage is. So pages here are linking to pages here. Central core is the section where all the pages are linking to each other, and then also linking to the pages in the out section, right? So it will be advantageous for a crawler to start somewhere in the blue area and as closer to the left as possible, right? So that was the idea. So this concept also helped. This concept of connectivity, strongly connected, weakly connected components also helped the early stages of web search engines to establish their indices, web index, crawling efforts, and so on. Okay. All right. Okay. So continuing on that, we discussed some definitions like lengths, the path lengths, and so on. Building on that, we have some more definitions that govern characteristics of the network, basically distance and diameter. So distance between any two vertices is the length of the shortest path between those two vertices, right? So you can think of this as if you're to travel from city A to B and there are multiple ways to get there, what is the shortest path so that you can get there quickly, right? If there is no path, then we call that as unreachable. You and we are unreachable, right? So those are special cases. But assuming that there is a path, let's say this is a connected graph where any two individuals are connected through a path, then you can calculate the distance between those two vertices. So you calculate all the paths, pick up the shortest one, right? Something that we already did a while ago with our example of path length here, right? So we saw that here we have multiple paths, but the shortest path was of length 3. So we can consider the distance between the red node on the left and the red node on the right. The distance is 3, shortest path length. Okay, so that is distance. Now distance is a measure between two individuals or two nodes. So it's a pairwise measure. So given a network, you can have distances between every pair of nodes. But to characterize the whole network, there is a concept called diameter, which is for the whole network, for the whole graph, which is defined as the largest distance between any pair of vertices in the graph. So which is basically coming from the diameter's definition in geometry. So diameter is of a circle is nothing but the longest distance, right, between 2 points in the circle. So diameter of a graph is nothing but the largest distance between any pair of vertices in the graph, which tells us what is the longest time it would take for information to travel in this network. These are the remotest points in the network. So if the diameter is, let's say, 2, we can easily say that within 2 hops, you can travel from any node or any individual in the network to any other individual within 2 hops. So that's a pretty well-connected graph. But if I tell you the diameter of a network is 100, it says that, okay, so there are 2 points here in the network that requires you to jump 100 hops to get to the other end, which then tells us that this is not a very well-connected graph, meaning the information will travel that much slower, right? So that's the concept of diameter. So lower diameter is always preferred in the sense that tells us how well connected that graph is. And especially if that graph is big, you have thousands of nodes versus just 2 nodes. diameter and size of the graph together help us understand the connectivity of the graph. Okay. All right. Now we have been saying a lot, and I'm sure by now you're convinced with the premise that the shorter the path or the shorter the distance, the faster things move in a social network, right? But is that really the case? Do you guys agree that the more connected a network is, the shorter the paths, the faster the information moves? You can say yes or no. Probably not. Okay. Nathan says probably not. Anyone else? And says yes. So the shorter the path, the faster the things move. James says don't think so. To check more people. Okay. Let's see if anyone else has any other thoughts. There are only two choices here, right? Yes and no. So you will be correct at least 50% chance. Okay. Well, we're moving on. So I'll give you some scenarios, and that basically stems from this very, very interesting theory from social sciences called strength of weak ties. Some of you may have already heard of it. This is a famous theory proposed by Mark Granovetter in 1973, where he was doing an experiment of folks who were in between jobs and how they were finding information about a new job or a new job opening, which they would consider applying to. Um, so from that experiment came out this very interesting conclusion that showed us in social networks the length of the ties actually do not make that much impact or influence the movement of resources, the movement of information. It is the quality of the ties. And even in that, weak ties, not the strong ties, not your direct acquaintance, it is the weak ties who you do not frequently communicate with are the ones who give you the most surprising or novel information. So most novel or surprising information will, or new information will travel through these weak ties, through these acquaintances who are not very frequently communicating with you. So that was completely opposite to what telecommunication networks tell us, what road networks tell us, where basically we are looking for shortest paths all the time, right? If you want to deliver network packets, then we are trying to figure out, okay, how we can reduce the path length so that our packets have, or the data has lower latency, lower delays, and all that stuff. Similarly, on road networks, how can we build faster freeways, more connectivity so that the traffic is less delayed? In social networks, completely opposite was observed, where so you can actually observe this in your real life. If you have siblings, you may get to know about your siblings from your friends, from your other family members, but probably not directly from your siblings. Sometimes that happens. So I don't know if you have observed that, but that is also sort of an interesting observation that follows the strength of weak ties phenomena. Okay. Yeah, and there are many other applications of strength of weak ties. In this, again, in the settings of studying collective actions, studying movements, studying protests, especially how resources are mobilized, how information moves, and not just within the same movement, but also between movements who share goals and who share aspirations, ideologies, and so on. So you may not be directly connected to those individuals, but just because there is a shared aspiration, goal, ideologies, the resources, information travel faster, right? So yeah, okay. So we have looked at a lot of interesting definitions, concepts on social networks. We have some more definitions, and then we'll get to the computational aspects. The next set of definitions will again adopt a more individual-centric approach, but it will show us how to know prestige, importance, centrality of individuals in the network. So sometimes we are looking for opinion experts, right? So how do we find those opinion experts in a social network, right? Or opinion leaders, social networks. So these the next set of slides will show us a way that even without looking at the content, you can still be with a fair bit of confidence know who are these opinion leaders, and so on, right? But before we get there, there are some more concepts that we have to cover, and then we will be able to understand those definitions. First is degree of a vertex. What is a degree of a vertex, right? Very simple concept. You're just counting the number of relationships a node is, or a vertex, or an individual is involved in. Or in other words, number of neighbors adjacent to the vertex. That is called degree of the vertex. If a vertex has no adjacent vertices, no neighbors, then the degree is 0. So in social networks, let's say Twitter or Facebook, you can think of this as how many friends, how many connections you have. That is your degree. Um, right. For directed graphs, we can consider two types of degrees. One is in degree, the other is out degree, again corresponding to the in and out edges. So a lot of people following you will consider as your in degree. A lot of people you are following in Twitter or X, that will be considered your out degree. Okay, so that is as straightforward of a definition called degree. Upon the concept of degree, we develop a measure called centrality, right? Which is looking at the importance of an individual, how well connected that individual is, right? And not just in social networks, you can also do this in other types of networks, like the road networks. You can see some cities are very well connected. You have a lot of freeways, roads coming into it, leaving. And then similarly, airports, you have a lot of hubs, a lot of flights flying in, leaving, as opposed to everyone else, right? So that's very typical in any social setting. So centrality can help us identify that. The most basic form of centrality is essentially degree counting. So how many edges you have, right, divided by the total possibilities. So again, this is a number between 0 and 1. So the higher, the better. If you have a centrality or a degree centrality of 1, that will tell us that you are connected to everyone in the network, right? So if there are 10 nodes in the network, 10 individuals in that community, and one individual is connected to the other 9, then their centrality would be number of nodes, number of edges, which is 9, divided by total number of possibilities of connection, which is also 9, exempting the person connecting with themselves, right? So loops are not allowed. So in that case, the degree centrality for that individual comes out to be 1. If an individual is not connected to anyone else, then their number of nodes or number of neighbors will be 0, or the degree will be 0. Then it becomes 0, degree centrality of 0. So this is always between 0 and 1. The higher, the better, meaning the more connections or more connected you are to the others. And then betweenness centrality are more advanced concepts. Closeness, eigenvector are even more advanced. And we will cover all of these in more detail the next few slides with equations and all of that and some visualizations. So that way you will know what does each of these measure govern. What type of centrality, degree centrality measures, what type of centrality betweenness measures, what type of centrality closeness, similarly eigenvector, right? And a little fun fact, eigenvector centrality is the most powerful measure in social network analysis, which is also adopted by PageRank in their Google search ranking. So you will see when we get there. Okay. So we covered degree centrality, which is basically counting number of neighbors you have divided by the total possibilities. That gives you 0 and 1. So that is the most straightforward, simple one. Betweenness centrality is a measure that looks at the number of shortest paths that go through that particular individual. So if you look at this network, you'll see a bunch of nodes. They're all colored differently. The nodes that are on the periphery of the network, they're all red. As we move closer to the center, you will see that the nodes start to turn bluish. So the color coding is basically showing the higher betweenness centrality. This is also a measure between 0 and 1. So you can think of some of these nodes like exactly this one has the highest betweenness centrality. What that means is if you pick any 2 points, the chances are the shortest path will flow through that individual. So this individual enjoys a very prominent position in the network, meaning if the information is traveling on these paths, then they will get to see that information, right? So they're serving as brokers of information in some sense, or bridges of information, right? Bridges between individuals or bridges between communities. So that's why betweenness centrality is that much more important. Um, Sometimes you will see that a node that has a degree centrality of 1 also has a betweenness centrality of 1. So there is a quite high correlation between degree and betweenness centrality. However, betweenness centrality sometimes can capture these very striking positions, very interesting positions and roles in the network for individuals. So if you're looking for individuals who can serve as good brokers of information or bridges across communities, then always adopt betweenness centrality as opposed to degree centrality. Okay. And this is particularly relevant in those networks where you will see a lot of communities, meaning a network which is fully connected, it will not make any difference. But if you have a fragmented network where you have pockets of individuals who are very densely connected among each other, but sparsely connected with the other communities, in those cases, identifying such betweenness centrality, high betweenness centrality nodes are more helpful than just the degree centrality, right? So fragmented networks use betweenness. If you have fragmented networks, use betweenness centrality. The third one is closeness centrality. And as the name suggests, the idea is let's find the individual who is closest to everyone. Again, you find the geodesic distance or the path, geodesic path from a particular individual to rest of the network, and then average it out. And then that gives you the average distance from that node to the rest of the individuals. And then you do this for all the nodes to identify who's the most central node according to closeness centrality, right? Again, the idea is the closer you are to everyone, the better, because everyone is either connected to you or is trying to connect it to you, probably because you are an opinion leader or you're a very well respected member of the community, or people follow you, people like you for various reasons. This person is considered as opinion leader or a leader in the community. So closeness centrality is also important. The last one, eigenvector centrality, which is the most powerful, also more sophisticated, as well as complex, takes a lot of time to compute. It's called eigenvector centrality. And as the name suggests, this is calculated using a mathematical operation called eigenvalue decomposition on the graph. I will go over this again when we get to the PageRank and search engines. We'll probably take some examples also, and if time permits, we'll do this by hand. But that requires matrix multiplications and all of that. So if you are up for the task, if you remember your matrix calculation and algebra, then we can do that. But otherwise, if you want to just understand this at a high level, then there is a matrix operation called eigenvalue decomposition, which when you apply on the graph, then it gives you those prominent individuals who have connections to other prominent individuals. In other words, eigenvector centrality identifies not just the number of connections, but also the quality of connections. So you are more important if you are connected to important individuals, right? So who you are connected to also matters along with how many people you're connected to. So quantity plus quality, right? So that's the idea of eigenvector centrality. And that is all done through this eigenvalue decomposition, which is sort of a recursive method of knowing your prominence based on the prominence of your neighbors. And then you can imagine if you need to know the prominence of your neighbors, then you need to know the prominence of their neighbors and their neighbors and so on. So this is essentially a recursive calculation on the whole network. That's why this is more complex and requires a lot of computational power on large networks. But nowadays there are a lot of approximations. In fact, we will be using some software tools which will just on a click of a button will give you eigenvector centrality scores for a network, right? But again, the fun fact, Google's PageRank is a variant of eigenvector centrality, where the page rank or the rank of a page is dependent on the rank of the pages that they connect to this page, and then further, right? So the same thing applies if you have a website and a lot of prominent or popular websites connect to your website, then your website is that much more popular. Okay. So essentially, you can think in terms of those popular websites driving or sending the traffic towards your website. So it is always important that you connect or you are connected to by other important websites. So if you're doing search engine optimization or driving or trying to drive traffic up on your website streams, then that is also one of the strategies. So if other important websites connect to you, then yes, your web traffic also increases. Right. Let me take a pause here and see. We have been at it at almost 1 hour 15 minutes. So if you guys have any questions, want to take a break, or want to continue. Okay. All right. It looks like Nathan, you are outnumbered. Right. I'm fine either way too. So if we would like to continue, we can, because some of the concepts, good. Some of the concepts that we are going to look at now are essentially building on what we have discussed. So these will fall in place much quicker. So if you have made it until now and you're still interested in the lecture, then I think the next set of slides will be easier. All right, so we have looked at variety of network, variety of graphs and all these concepts, and it was very easy to understand those as humans. But how do we make computers understand this? That's the challenge, right? How do we program computers to count degree centrality or calculate eigenvector centrality? Or even identify those groups or communities or subgraphs, paths, path lengths, distances, diameters, whether the graph is connected or not, whether it's a clique or not. How do we do all of that from using computers, right? Using algorithms. So in order to do that, the first thing is you have to represent this information, the graph information, in a way that computers can understand, they can read it. So we have different types of structures, primarily two types that we can use to store the graph data. One is a list structure, and as the name suggests, it is just nothing but a list of edges. We will see that. The other is a matrix structure, which is a little bit more refined form of representation. Also takes more space, but we will see what those matrix structures are. Right. And these are primarily the two structures, and we will also compare the strengths and limitations of each of these, which one is more popular versus less popular in algorithms or software programs that we use these days. But we'll first start with the list structure, which is again the most basic form, where you have a list of edges, which is written as, so if you remember that example of 4 vertices, which we started from V1, V2, V3, V4, a very simple graph, 4 vertices, 4 edges. The way we are writing the incidence list structure is in this format. The forward slash here basically represents OR. So it could be written as V1, V2 or V2, V1 since it is undirected, does not matter. V2, V3, V3, V2 or V3, V4, V4, V3 and so on. Basically you're representing the graph. You're telling the computer that this is a graph where these many vertices V1, V2, V3, V4 and all the edges are listed in this format. If it was a directed, then of course the direction would make sense. So V1, V2 would suggest that the direction is from V1 to V2. Okay. So that's how we can store the incidence list. Nothing but a set of edges, list of edges. That's it. Adjacency list is basically a little bit more structured way of writing the same information where you are providing not just a list of edges, but list of adjacent vertices. For instance, for V1, we mentioned that V2 and V4 are the adjacent vertices. So V1 colon V2 V4. For V2, the adjacency, the adjacent vertices are V1 and V3. For V3, we have V2 and V4. For V4, V1 and V3. Right, straightforward. If it was directed, then of course this would modify. So if there was an edge between V1 and V2 directed towards V2, then this edge, let's say if it was directed towards V1, then it would be different. Then the adjacent vertex for V1 would be only V2 and not V4. Okay, so direction always makes a difference. So since this is undirected, it does not matter. V1 has both vertices as adjacent vertices, V2, V4. But if the directions were specified, then you would have to consider that. Right, so adjacent vertices would change accordingly. All right. Okay, let's see if you guys can give me the list structure representation of this example. So we have vertex V1 connected to V2, V3, and V4. So how will the adjacency list look like in the incidence list? You can use the chat window to type. Yeah, both actually. So incidence list as well as adjacency list. So try the incidence list as well as the adjacency list. And again, incidence list is nothing but the list of edges that you see in the graph, but making sure that you're capturing the directions. So I'll give you a starting point. So first entry in that list for the incidence list would be V1, V2. And then there will be two more entries which anyone can type. And let's see if you guys get this concept. And if it helps, I can go back here to show you how they, yeah, just type in the chat. That's okay. So this is how it looks like for incidence list, just the list of edges, right? So here in this example, we have 3 edges. So there will be 3 items in the list. I've already given you one item, which is V1, V2. What will be the other 2 items in that list? Yep, absolutely. So Vishwa says V1, V3, V1, V4. So the adjacency, sorry, the incidence list for that would be V1, V2, comma, V1, V3, comma, V1, V4. That will be the incidence list structure. Okay. So incidence list structure for this example will be V1, V2, V1, V3, and V1, V4. And you notice that we didn't say V1, V2, or V2, V1 because we are respecting the directions. So we cannot discard the directions. So the direction is always from source to destination. So we always put the source first and destination second. Now the second is adjacency list. So again, use the chat window and then type your responses, how the adjacency list representation will be for this example. And if you want a refresher, then I can give you the slide. So this is the adjacency list. So for V1, V2, V3, this example, again, this is undirected. So for undirected, this is how the list structure looks like, where we are recording the adjacent neighbors, the neighbors that are adjacent to each node. In this case, V1's adjacent nodes are V2, V4. For V2, V1 and V3. For V3, V2 and V4. For V4, V1 and V3. Okay. Yep. So that is, so James says V1 colon V2, V3, V4. For V2 to V1. Yeah. Okay. So James, just a quick correction on yours. So if you look at the direction, and this probably will help others as well. If you look at the direction, the adjacent neighbors are only for V1, right? So V1 can see V2 and V3 and V4. But when you are at V2, you don't see adjacent neighbors because the direction is not towards V1, the direction is towards V2. So that's why V2 does not have any adjacent neighbors. Again, adjacency or adjacent neighbors are basically those neighbors who you can reach. So if the direction, so think of this as a one-way street. So if you can travel from V1 to V2 and it's a one-way street, you cannot travel from V2 to V1. So directions are governing that. So again, so some of the other students, Richa has said V1 to V2, V3, V4, rest are null, that's correct. Bishwa has the same, Anne has also has the same. So Anne is also, yeah. So that is exactly the solution for this, right? Okay. Okay, so Hakan has asked a question which is actually answered in the next few slides. So when we discuss different types of structures, right? So first we are looking at incidence list and adjacency list and within the list structure. When we start looking at the matrix structure, then you will see completely different forms of representations. And then you will compare which one can be used and which one is more convenient to use. But this is the most easiest and also most space efficient. So yeah, you will see those differences. So for list, there are only two. We have covered both the list structure types, and you guys were correct in your findings, in your responses. Now we come to matrix structure. Matrix structure also has different types of data structures. So first one is incidence matrix, where you are actually constructing a matrix of vertices and the edges, right? So vertices are on the rows, edges are on the columns. So if you look at this example, and of course here you have to annotate the edges also, otherwise how will you put the column headers? So for the same graph, 4 vertices, 4 edges, you have marked as 1 and 0 if that particular edge connects the two vertices. So in this case, V1 and V2 are connected through E1, so you put 1 in both, right? And then we will also see how this impacts if the network was directed. We will see that example also. And then for the rest, you can see that for E2, it connects V2 and V3. So for E2, we have one in V2 and V3, but the others are zeros. For E3, we can see there is an edge E3 that connects V3 and V4. So we go to E3, we have an edge between V3 and V4, rest are zeros. Similarly for E4, that's connecting V1 and V4. We go to E4, we mark 1 on both those vertices, others are 0, right? Same information, but you can see how differently it is captured here. And it is also telling us, this is not as space efficient, because when you looked at the incidence list, it was just 4 items in the list, right? So if you do some type of bit calculation or byte calculation, you'll see that this would require more storage space than the other. And again, we are looking at a very simple example of 4 vertices and 4 edges. But if it was a complex example with billions of nodes, billions of edges, then you can imagine how complex this matrix would look like, right? However, when you look at this matrix, if you were to calculate degree of a vertex, again, degree is number of edges on it, right? It is very straightforward. You just look at the vertex and then start calculating here, row wise. I can see that there is one edge and then another edge, right? 2 edges. So without even looking, if you hide the network, that you don't have access to the network, you just have the access to the graph, to this matrix, you can easily calculate the degree of each of these vertices without even looking at the network. So just do a sum of the rows. So for V1, if you add up all the cells in the row, 2. V2, again 2. V3, 2. V4, so, right? So that tells you the degree of what it is. So that is where the convenience lies. Yes, you pay more in terms of space, but computationally, it is very quick to know how what's the degree, right? And many other operations also become that much easier, such as community extraction, centrality measurement, and so on. But that is not the only matrix representation. We have another one, which is called this adjacency matrix. Adjacency matrix is more popularly used, not just in social computing or computational social science, but also in traditional social sciences. And we will take that example also when we get to sociometry. Right? Okay. So when we look at adjacency matrix, this is again the kind of a similar thing where you have a matrix representation of the graph where you put vertices on both rows and columns. And you try to denote the pairwise relationship using row and column pairs. So if you look at V1 to V1, there is no self edge. There is no edge between V1 to V1. So we put a 0. From V1 to V2, we do see an edge. So we put a 1 there. From V1 to V3, we don't see any edge. So we put a 0. From V1 to V4, again, we see an edge. So we put a 1, right? And we follow the same logic for the rest of the rows, and then you put ones and zeros in the cells corresponding to the edges. Straightforward. Okay, this is an undirected graph. There is no direction. So it does not matter when you look at V1, V2 or V2, V1, you will always find the same entry. So let's check. V1 to V2, there is a 1. V2 to V1 is also there is a 1, right? In fact, when you look at the diagonal, you will see that it is completely symmetric on either side of the diagonal. So this is called a symmetric matrix because this is undirected graph. It does not matter whether V1, V2 or V2, V1. Similarly, V2, V3 or V3, V2. The above diagonal entries are identical to the below diagonal entries. So that is a property called symmetric matrix property. Okay. Again, if you look across the diagonal, the above diagonal and below diagonal are identical. Right. And this is very specific for undirected graphs. If this was a directed graph, then we may not have a symmetric matrix. Okay. So that is a very important distinction in the matrix structure. So if it is an undirected graph, then it will be symmetric. If it is a directed graph, it will be asymmetric. Okay. Now I realize that it'll be difficult for you to write this adjacent symmetry in the chat. So what I'll do is I'll just skip over this as an exercise and just go over the solution so that you understand how to write the matrix structure for this example. Now this one is directed. Previously, when we looked at the examples, those were undirected. So when you look at the directed graph, especially in the incidence matrix, you notice some differences. So when you look at this one, right? So we have V1, V2, V3, V4. Only V1 is connected to V2, V3, and V4 through E1, E2, E3 respectively. So we set up the matrix. Again, rows are your vertices, columns are your edges. So we have 4 vertices and 3 edges. And then you can see that the direction is from, again, source to destination from V1 to V2. So as opposed to putting 1 on the both, we are depicting the direction using -1. So from V1 to V2, the edge E1 is connecting V1 to V2. So the source is -1 and destination is 1. Right? Same for the other edges. E2 is connecting V1 to V3. So V1, the source is -1 and V3 is +1. Similarly for E3, V1 to V4. Right? That's the idea here. So that is incidence matrix representation of this directed graph. When you look at the adjacency matrix, since we are not denoting edges, we are just putting vertices with vertices on the rows and columns. You don't have to worry about negatives anymore. Why? Because this will capture the direction. So when you look at V1, the first row and the columns, so since we don't have any self loop, V1 to V1, there's no edge. So we put 0 here. But from V1, we can see that there is an edge to V2, there is an edge to V3, and there is an edge to V4. So we put 1 in each of those cells, right? But there is no other edge left, right? 3 edges are there, 3 are covered. So rest of them are 0. So again, here you won't see an entry from V2 to V1. So when you look at from V2 to V1, there is a 0 because V2 cannot go to V1 because the direction prohibits that. Right? Similarly for V3, you don't have any edges from V3. There are no edges from V4 either. So all of them are zeros. Right? And this again goes back to our symmetric and asymmetric matrix properties. Since this is a directed graph, you will notice that above diagonal entries are not identical to the lower diagonal. So while the above diagonal entries are all ones here on the first row, the lower diagonal, you don't see ones here. Right? When you looked at the previous example here, they were identical, above diagonal and lower diagonal, almost like a mirror image. If you fold this matrix along the diagonal, you will see complete, mirror image. Okay. All right. Any questions so far? Awesome. Good. Now the fun begins. How we can use these matrices to do all the interesting things that we looked at before, right? We looked at degree centralities, communities, path length, distances, all of that thing, right? So we have gone through all this rigorous representation and understanding. How does this help, right? So let's start looking at these things, such as degree. First, we know that there is a concept called degree, which is sum of the adjacent nodes or adjacent your neighbors. We can do that here very easily. Let's take a simpler example first. If you were to calculate degree of vertex 1, right? So let's do this way so that you don't look at the network, just look at the matrix alone. It is very easy, right? Just count the ones in the row or just add the row. You'll see for V1, the sum for the row is 2. For V2, the sum is also 2. For V3, again 2. For V4, again 2. That means all these nodes have same degree, 2. They have 2 neighbors. And if you actually come back to the network, that's what we have here. Right. So now you don't have to manually count. You can just write an algorithm that, hey, do this, just do a sum of the rows, and then you'll have degrees, right? So once you represent in this matrix format, it's very simple for writing programs, algorithms to do all these things, right? So, but this was a simpler case where you had no directions, nothing, right? But if it was a directed graph, like we had looked at another example, this one, things are not as straightforward. Again, it's the same thing that let's say we try to hide this, the network, and then look at the matrix alone. If you look at this matrix and count the row for V1, you end up with the value 3, right? 1 plus 1, 3. That means the degree for V1 is 3, but every other node has a 0 degree, right? That's how you see it, right? Okay. When we come back to the network, we can actually see that here. So for V1, we see that there are 3 adjacent nodes, 3 adjacent neighbors. V1 can reach V2, V3 as well as V4. So the degree 3 is accurate, right? That we calculated as the row sum. But we were not able to qualify that as an out degree or in degree. So for that, we have to further understand when you calculate the sum of the row, that is telling us how many connections, how many nodes you can reach. So how many connections V1 can reach, meaning out degree, edges going outside of V1. But if you calculate the column sum, then you will get to know the in degree, how many edges are coming in or inwards to you. So if you do the column sum, for V1, it is 0. For V2, V3, and V4, there is 1 incoming edge each. If you do that sum, right? Column sum. And we get back to the network, you will see the same thing. For V1, there is no incoming edge, so that's what the column sum shows 0. But when you do the column sum for V2, V3, and V4, then you will see that 1 each. That means each of these nodes have 1 incoming edge. So now your concepts of out degree and in degree are also well defined in this adjacency matrix. So you don't have to look at the network, just choose the row sum or the column sum to get out degrees or in degrees respectively. Okay. Let me know if this is clear or else I can go over this concept again. Okay. Okay. Cool. All right. So the next concept is even more interesting. Right? This is amazing. It's almost like a magic. So remember our connectivity concept, whether two individuals in a node in a network are reachable or not, right? So it turns out that if you multiply the matrix with itself, then you will get to know whether two individuals are reachable in 2 hops. If you multiply 3 times, then you will get to know whether two individuals are reachable in 3 hops. You keep doing the math, let's say n times, you will find out whether any two individuals are reachable in n hops. So in other words, if this was a very complex network, imagine that there are billions of edges, billions of nodes, it would take you a lot of time to manually just to sift through the network to know whether V1 is connected to, let's say, V100 or V1000. You'll have to literally, just zoom into the network and follow the edges, keep pointing to the edges and hope that you don't lose the path and you get to V1 and from V1 to V100 and then count whether they are reachable or not, or how many hops lie between them, how many vertices lie between them. But all of that work has been made simpler if you just multiply this matrix with itself and keep doing that for n times. So let's say if you want to know which individuals are connected in 1 hop, 2 hop, 3 hop, 4, 5, n, or maybe 6 hops, and then you want to stop, you just keep doing the math and you'll know that. In fact, I have an example here. So for the same thing, V1, V2, V3, V4, that JCC matrix is this. When you multiply A with itself, then you get this matrix, which is A squared, A times A. And you can see that, again, you discard the diagonal, right? Because diagonal, we know that there is no self loops, V1 to V1 and so on. You can see that from V1 to V3, we have a 2 here. V1 to V3, it tells you that yes, they are connected in 2 hops. And actually the path is also 2. Similarly, V2 to V4, there are 2 similarly, right? And V3 to V1, V3 to V1, 2 hops. V4 to V2, 4 to V2, also 2 hops, right? And again, you have to discard the diagonal because diagonal does not count because we are not looking at the self loops, right? So this tells you that just by multiplying with itself, you will know whether two individuals, V1, V3, are connected within 2 hops or not. If you repeat this example for n number of times, you will get to know that many times or that many hops connectivity. So if you want to do this for 3 times, then you will see that V1 is connected to V4 with 3 hops, although there is a direct edge also, but you will see that when you do that math, V1 and V4 are connected with 3 hops. So, right. So if it was a larger network, then you could have done this even more number of times, and then you would have seen all the individuals who are 1 hop away, all the individuals who are 2 hops, 3 hops, 4, and then n hops away. And then you can start to build your average path length in the network. Right. So all of that is made possible by just multiplication of the adjacency matrix with itself. Okay. All right. So we looked at 2 types of matrix structures, incidence and adjacency. It turns out that there is another one, which is a distance matrix, which is similar to adjacency. The only difference is instead of specifying 0 or 1, we specify the distance, the shortest path between 2 nodes, right? So that's the basic difference. Otherwise, it's the same. Okay. Now, when you compare these, and I'm sure by now you have already started to mentally mapping these to different data structures, and I'm sure you have some sense of the strengths and limitations of each. But just to distill them here, list structures are more memory efficient. As you can see, you don't need that much space, especially for large networks, large data sets, very quick. However, the lookup is slower. If you want to know whether an individual is connected to any other individual in a matrix, it's just a single order of 1 lookup. You go to that matrix, go to that cell and row, and then you find out. In list structure, it is much complicated. You have to parse the list to know whether this is a connection or not. So you can use hash index structures to speed it up, but still it is slower than matrix structures. These structures, with all the limitation, they are used by a lot of visualization and analysis tools, especially when you're dealing with large networks. Okay, so matrix structures are good when you have either extremely fast or supercomputers or big data centers or some advanced approximations that you can apply to the networks, right? Okay. All right. How are we doing? Good, good, good. All right. what we can do is, I believe we have kind of 20 odd more slides. So I will try to cover communities and social networks and stop after this because I don't want to rush into some of the specialized concepts towards the end of the lecture, which are also equally interesting, um, because you never know which type of concepts might pique your interest, and you may want to do your course project into that. So we will cover the communities in social networks, some algorithms that we have in the slides, and then that will be the end of this lecture. And the remaining lecture we can pick up in the next class. All right, so we have talked about groups of individuals in social networks, right? Subnetworks or subgraphs. While looking at the visualizations, and I will have to go back to my visualization slide up front here. By looking at these slides manually, it is easy to see or locate these communities or these clusters. But the challenge again lies when you are trying to extract these things computationally, right? This is still easier to do manually because we have a very small network, very well color coded and so on. So, it makes our life very easy to detect these communities. But imagine if this was a giant hairball and it was everything was not as evident as it seems like here. So how would you train or tell a computer to extract these clusters or communities that almost appear to self-emerge based on their connection dynamics within themselves or across different groups? How do you tell a computer to do that? Right. So that's where community identification, community extraction algorithms come to our rescue. So we'll take a look at one example. And again, this would require a little bit of knowledge of math if you want to program this algorithm. The good news is you are not required to program any of these algorithms. Most of the tools, in fact, almost all the social network analysis tools have these algorithms inbuilt. So you just have to throw your network to them and click a few buttons and it will give you these clusters. But again, I always go through the fundamentals also so that you can understand the concept and not just um, use the software, so you understand what the software is actually doing behind the scenes. So sometimes if you have to tailor the software to your needs, how to do that, right? So not considering this as kind of a black box approach, we want to make sure that we understand how all of this is working, so that when we interpret the results or do parameter tuning, we are that much more aware or informed of our decisions and choices. All right, so this is the basic algorithm for identifying communities in a network. This is called spectral clustering, and the name will become clearer because it uses spectral calculations and matrix decompositions that will allow you to extract those components in the network or communities in the network. The whole idea behind this is, at a fairly high level, is looking at connection behaviors, meaning which set of individuals or nodes in the network have dense connections between each other or within themselves versus the rest of the network. Okay. So the more interconnections among themselves as compared to the rest of the network, that means that there is a group or group behavior within this set of nodes, right? But in order to do all of that mathematically or computationally, we have to go through some matrix operations on the adjacency matrix. So if you recall your adjacency matrix description, which is nothing but a square matrix of vertices on the columns and vertices on the rows, and then zeros and ones in the cell, depicting whether two nodes are connected or not. You depict that adjacency matrix with W, and you specify how many clusters you need, let's say k number of clusters. Then, first of all, you compute a diagonal matrix called D, which is nothing but the sum of the rows. For each row, you do the sum and put the value in the diagonal, right? and then compute the graph Laplacian, which is L, the graph Laplacian L, which is D minus the W, the adjacency matrix. This ensures convergence. So convergence meaning, again, this is going to do eigenvalue decomposition. So if you remember the little discussion we had about eigenvector centrality, this is a recursive process. So a recursive process is only good if it converges. If it does not converge, then it can oscillate between multiple states, and you will never know which is the correct solution. Neither could be correct solution. So you need to make sure that this solution will converge after a certain number of iterations. So in order to do that, we calculate this graph Laplacian L equals to D minus W, and that then is subject to eigenvalue decomposition, and we pick the first k eigenvectors. K eigenvectors is basically the number of clusters you want from this network. Okay. Now, a question usually is that how do we know k even before we do the clustering, right? So given a network, do you already know that there are 10 clusters or 11 clusters or 9 clusters? How do we know what is a good value of k? So there are known heuristics to govern that. And anyone who has done or taken any supervised machine learning or data mining course, then you know that there are methods like silhouette scores or elbow method, where you try for different Ks, and then you look at the cluster quality, and then where you see the highest cluster quality, you pick that K, right? So those are known methods, but again, why I'm telling you all of this is just so that you understand or build that fundamental knowledge about clustering, network clustering. But when we take this to the software, when we use software like Gephi or NetworkX in Python, you would not be bothered with all these details. You will just provide the network and ask it to cluster. It will give you the right number of clusters. It won't even ask you the number of value k, right? So it calculates all those things on its own, and then you just get to see the final clustering. But now, with this knowledge that you have that much more appreciation for those algorithms and understanding. So you will be able to explain those results better. In fact, we will take an example to show a sort of a toy example, and we will walk through these 5 steps and then show you how those clusters actually emerge after all this matrix manipulation, right? So we'll take that example. All right. So again, just reiterating that given a network like this, the goal is to identify meaningful clusters. When we look manually, yes, it kind of appears that there are 2 clusters, one big in the center, the other one kind of small towards the corner in the left. So yeah, but manually, yes, it is easy to understand. But if you have large networks or some visually impaired or challenges, then it will be difficult to do that. So that's where, again, computers come in handy. So looking at this toy example of a blog network where you have 9 blog sites, right, B1 through B9, and the connections, again, this is very, very straightforward. You have 9 blog sites and connections are depicted here. So when you just look at the blog network without even looking at the adjacency matrix, you can easily see, right, that there appears to be 2 communities. One community has these 4 blog sites, and another community has these 5 blog sites. But again, this is a simple example, but imagine if there were millions of blog sites here, it would be very difficult to see or perceive these clusters. But now you know the cluster configurations. That first cluster has B1 through B4. The second cluster has B5 through B9. Now when we do the matrix manipulations and all the computations that we had seen before, and when we look at the final clustering, you will see that exactly this emerges as an outcome of those matrix operations. So now we'll start with the matrix. I'm not going to go over how this adjacency matrix built, but you can just imagine the adjacency matrix that we discussed before. This is how it is constructed. So from B1, what are the other nodes that are reachable? Again, this is undirected. We kept it simple. So B1 is connected to B2, B3, B4, And that's what you will see here. B1 is connected to B2, B3, B4, rest all 0. And so on and so forth, right? So you can see for B2, B3, B4, and other nodes, how they're connected. So this is nothing but the adjacency matrix. We call this as W. Now, if you go back to the sequence of steps, first you do the W, then compute the diagonal matrix, then calculate the graph Laplacian, and then do the eigenvector and so on, right? So we'll walk through those steps. So first is the matrix W. Second is the matrix D, which is nothing but the diagonal matrix where you add up all the values in the row and put that on the diagonal. So if you look at this one, first row, there are 3 ones. You add it up, put it on the diagonal. So add those up, put it on the diagonal, the rest are 0. Same thing you do for the rest of the 8 rows. B2 to B9, so you have the diagonal matrix, right? We call this as D. L, which is the graph Laplacian, is calculated as D minus W. So matrix D minus matrix W. So this is a linear operation, cell by cell. So you just do subtraction cell wise. So in this cell we have 3. If you look at here, we have 0. 3 minus 0 is 3. Go to the next cell, there is a 0 here. Look at this next cell, there is a 1 here. So 0 minus 1, negative 1, right? So you do this for all of that. Again, of course, you can put a computer to this as opposed to doing manually, so that will be much faster. The moment we do this, you already start to realize something. If you look carefully at this matrix, you will actually see 2 blocks here. And these 2 blocks of numbers actually correspond to those communities. So first block is B1 to B4. The second block is from B5 through B9, right? So, but we are getting closer. This is not the end goal, but you can see that it is emerging, right? These type of things are emerging communities. The third step was to calculate the eigenvector decomposition. So again, you can use any eigenvector decomposition process in Python or MATLAB. It just requires a square matrix. You provide this and then ask for it to be eigenvalue decomposed. And then you look at the top k eigenvectors. So if you want to do 2 clusters, then you look at the top 2. If you want to look at 3 clusters, 4 clusters, and so on. Right. In this case, let's just do 2 eigenvectors, the first 2. And if you want to know more about eigenvector decomposition, I can probably have a separate lecture on that. The main idea here is to represent a higher dimension information. Here you have 9 columns, meaning 9 dimensions of this information, to lower dimension vector, which is just 2 dimension, right? So what you're trying to do is to compress the information. So think of this as like a zip archive utility. You have a big file, you're trying to compress it into a smaller file where the information loss is minimum. So as you keep adding more and more eigenvectors, you will achieve minimum loss, but you will require that much more dimensions to represent the information. Another way to think of this is, if you look at these 9 dimensions and you try to visualize a 9-dimension space, it is almost impossible. After 3, we give up, right? 3 is the maximum we can visualize. Now what we have done is we have put this in 2 dimensions. We have compressed all those 9-dimensional information to just 2 dimensions, which you can visualize easily on a scalar Euclidean space like this one, where you have x and y vector, right? X and y axis. And you throw these points. So basically, these are your data points and consider them as x and y coordinates. So you have B1, B2, B3, and B9. And each of these blocks actually have x and y coordinates in this Euclidean space. That's what you're doing, right? So you can see that for B1, B2, B3, B4. So only B2 has a little bit of variation on the y-axis, or EV2, eigenvector 2, but the other 3, B1, B3, B4, are kind of superimposed top of each other. So this is B1, B2, B3, B4. When you look at the rest, B5 through B9, you will see that B5, B6, B7, B8 are identical coordinates. So they are on top of each other. B9 is different. So let's say when you look at this alone, right? Forget about the eigenvector. When you look at just this Euclidean space, two-dimensional, you can easily say that, well, looks like that these two or these 5 points, because four are here and one is here, kind of, are closer to each other than these. So we can consider them as one cluster and these four as another cluster. You don't even have to do much. You can just run a simple k-means or any type of simple clustering to identify these communities, right? Community one and community two, right? So that is this magic, right? All this matrix computation, manipulation, operations, and then you do eigenvector decomposition, and then we throw them on a two-dimensional space, it naturally appears, right? It may not be as easy for a complex network. You may have to do 3 or 4 eigenvectors. But again, the idea is you can just do a quick k-means or any clustering, it will give you the communities. And here, when you do clustering, either you can specify the clusters or you can let the algorithm decide what is the optimal value of clustering.